we're going to try to more understand the structure of certain combinatorial objects. Okay, so this is a joint work with Sarah Browner, Zaj Dawarty, and Anna Schilling. And this was started at Banff in 24 and then continued at IES in 25, where we had the pleasure to be able to meet as groups of women and work together. Okay. And I guess we were a bit excited, so we took a photo with Einstein at the IES. So, but I'm not going to talk much about Einstein. Okay, we're going to stay a bit more low level today. Okay. So anyway, so I'm going to take it slow. I'm going to start with quite a long introduction to try to explain to you why we want to do these sort of things. But if there's something that's not clear during the talk, you should really raise your hand and stop me and making sure that what I'm saying makes sense. Okay? So we're going to talk about a lot of combinatorial objects related to algebraic combinatorics, but as you'll see, most of them are quite classical. So I think you should be able to follow easily what I'm going to try to say today. Okay. So, and first I'm going to start by doing a couple of self-advertisement of two things I'm going to organize in 26 and 27. So first, there will be a summer school in Paris during the third week of June. That's mostly targeted towards so if the sound is not good.
To me is very good.
Oh, okay. So, and so it will be mostly in enumerative combinatorics, but also in relation to integrability. So you should come to Paris. And also we'll do a full semester at SL Math in Berkeley during the fall 27. And applications will be due for this in a year, okay, at the beginning of the fall 26. Okay, so if you'd like to come and spend a semester at Berkeley, you should think about that. Okay, so let me start with my introduction. Okay, so I'm gonna, as I said, I'm gonna start slowly. So one of my main objectives this talk is gonna be integer partitions. So what's an integer partition? It's just a sequence that here I will always think of into n parts when n is a positive integer. Okay, so it's a sequence of non-negative integers and the order doesn't matter. So I'm going to think of them as weakly decreasing. Okay, and so here, for example, if n is equal to 4, 4, 3, 1, 0, okay, is a partition because this is weakly decreasing and I have 4 non-negative integers. Okay, and I'm going to draw these partitions with a Ferraz diagram. So I'm going to do it the French way, but I like every way, so don't be offended. Okay, so I'm going to number the rows from bottom to top. Okay, and then I'm going to first put 4, because my first part is 4 cells, then 3 cells, then 1 cell, and then 0 cell. Okay, and so it's just a way of drawing my integer partition. Okay, and sometimes I care about which integer I partition. Okay, and I'm going to say that lambda is a partition of n, is the sum of the lambda i's is equal to m. So here my partition was a partition of 8, because 4 plus 3 plus 1 is equal to 8. Okay, but what I'm going to be interested in is actually not even symmetric function. I want to study some symmetric polynomials. Okay, so n is my same n as before. So I take a permutation of 1, 2 up to n. So here, for example, if n equals 3, my permutation could be 3, 1, 2. And I'm going to take a polynomial in n variables, and I'm going to say it's symmetric, okay, if I permute the indices of my variables, okay, and I still get the same polynomial. So for all permutation, my polynomial in x1 up to xn is going to be equal to the polynomial now where x1 is replaced by x sigma 1, x2 by x sigma 2, etc. Okay, so here I give an example of a homogeneous symmetric polynomial of degree 3. Okay, and you can see that here I have an x1 squared x2, and I can do any permutation and find all the monomials with first a power of 2 and then a power of 1. Okay. And so, as probably you all know, the basis of symmetric polynomials of homogeneous degree m is indexed by integer partitions of m, and there are many bases of that. And here I will just study 2 bases today. So the elementary basis, so E, if it's indexed by an integer k, okay, it's just a sum on all the increasing sequence I1, I2 up to ik, where I sum all the monomial xi1, xi2 up to xik. And if my partition is not, has more parts than 1, okay, I just multiply E lambda 1, E lambda 2 up to E lambda n. And then the Shor basis, okay, that will be my main interest. So it's again indexed by a partition of m. It's in n variables. And I can define these Shor polynomials into many ways. And for example, I can define it as the ratio of 2 determinants, where here the denominator is the van der Monde determinant. Okay. But it's going to be mostly a combinatorial talk. Okay, so there's many other ways, as I said, to define a Shor polynomial. And what I will be mostly interested in today is to see the Shor polynomial as what we call its combinatorial interpretation. So I'm going to sum on a bunch of combinatorial objects, and to each object, I'm going to assign a monomial, okay, that I'm going to call x to the t, okay, and those objects, you all know them. Okay, we take the Ferraz diagram of the partition that's indexed as a Shor polynomial, and now we're going to fill the cells of the diagram with integers from 1 to n, okay, where n is fixed here. And I have the condition that this will be weakly increasing in row and strictly increasing in column, okay? So here is such a valid filling of my Ferraz diagram, and I sum on all the possible fillings with integers 1 to n, and I have to tell you just the weight of each tableau, okay? So given a tableau, I'm going to associate it a monomial, and I just count how many 1s I have, how many 2s I have, how many 3s up to n. So here, for example, we count the number of 2s, 1, 2, 3, 4, and that's why we have an x2 to the 4 in this monomial. Okay. So this is extremely classical. Okay, but now we can ask some very natural questions. Okay, so if you have a family of symmetric polynomials and you'd like to know how you can expand in those spaces. Okay, so I have my symmetric polynomial f here. Okay, how can I expand it into the Shor or the elementary basis? And especially we're interested in answering this question when these coefficients here are non-negative. Okay, and if they are non-negative, we would like to give some combinatorial interpretation of these coefficients. So let me give an example, okay, that had a lot of publicity recently, which is the chromatic symmetric function. Okay, so this is not a new object. This appeared about 30 years ago. So you start with a graph G, and this graph has exactly m vertices. So here I gave an example of a graph with m equals 5. So I have my graph with m vertices. And now I have n colors. Okay, and I'm going to color the vertices of my graph, but I want to properly color them. So what do I mean by proper coloring? I mean, whenever I have an edge between 2 vertices, then my colors need to be different to have a proper coloring. Okay. So here is an example of such a coloring. Okay, so I colored 1 and 4 in purple, 2 in red, and 5 in yellow, and 3 in green. And this is a proper coloring because whenever I take an edge between two vertices, then these vertices don't have the same color. Okay, and now how do I build my chromatic symmetric polynomial? Okay, so I'm going to give now a monomial to each proper coloring of my graph. So I sum on all the proper colorings of the graph G, okay? And then I'm going to record the color of C1, the color of 1, the color of 2, up to the color of M, okay? And I associate a monomial to each proper coloring. So this is very easy to see that this is indeed symmetric because you can see that I could have switched, for example, purple and yellow, and that would still have been a proper coloring. Okay, so here is an example of a graph here. So I claim that if I looked for this graph of the chromatic polynomial in two variables, it's going to be equal to 0 because I don't have any proper coloring with two colors. Because here we have a triangle, so these three vertices must have distinct colors. Okay, but if I look at the chromatic polynomial in three variables, and then I'm going to get this big polynomial here. Okay, and it's very easy to see why I get that, because if I fix the color of my central vertex here, okay, then this can be any of the other two colors, and this also can be any of the two colors as long as they're distinct. Okay, so once I fix this, I get this, one of these three things. So the definition is simple. The fact that it's symmetric, it's simple. Okay, but for certain families of graph called the unit interval graph, okay, it turns out that these things have nice expansion into the Schur and elementary basis. Okay, so what's a unit interval graph? So the intervals, so they are of unique length. Okay, so each interval is of unit length, and they're going to correspond to the vertices of my graph. And then I'm going to have an edge between two vertices if the interval intersect. Okay. So for example, here 1 and 2 have a non-empty intersection, so I have an edge between 1 and 2. Okay, and shortly after this definition of the chromatic symmetric polynomial, Gasharov proved that if I looked for a unit interval graph of the Schur expansion of this symmetric polynomial, and it's always non-negative, okay? And he gave a beautiful interpretation in terms of some tableau. But for a very long time, okay, it was conjectured that it was also E-positive. And many people tried to work on that, on some special cases, some relation with also some algebraic geometry. And it's this year, I guess last year, that there was a very beautiful proof by Hikita, who proved that if you expand this chromatic symmetric polynomial in the E basis, then the coefficients are non-negative. Okay. And quite surprisingly, everybody was trying to prove this using some kind of orientation of the graph. What he did is he defined these coefficients, d lambda, as certain weights on standard Young tableau of shape lambda. Okay, so that's my way now to define what a standard Young tableau of shape lambda. Okay, so because I'm going to need them. And it's going to be just the same as the semi-standard Young tableau of shape lambda that I just defined, except now that each integer appears exactly once and just once. Okay, so now if my partition is a partition of 8, like in my example, I'm going to put the numbers 1, 2, up to 8. And it's going to be such that they're strictly increase in rows and columns. So, and in this talk, I'm going to be interested in those standard Young tableau of shape lambda, but I'm going to be interested in a special statistic on them that I'm going to define now. And this statistic is the notion of a descent of in a standard Young tableau of shape lambda. Okay, so it's not a new statistic. It's been done before. Okay, and I'm going to say that I is a descent of my tableau even only if I plus 1 is in a row above I. Okay, it's not to its right, it's not below, it's above I. Okay, so let's look at this tableau. So 2 is to the right of 1, so 1 is not a descent, but 3 is above 2. Okay, so 2 is a descent, and then 4 is a descent, and 6 is a descent. Okay, because here we can see that 7 is above 6. Okay, so given a tableau, I get a subset of 1 up to m minus 1, and we all know that there's a bijection between composition of m and subsets of m minus 1. Okay, so now I can go from my subset to my composition, okay, where I would get now as a partial sum. So I'm going to get 2. Oops. No, sorry. Maybe it's a bad idea to do that live. Okay, so 2, 2, 2, 1. Okay, so, and now the subset is the partial sums of my compositions. Okay, so now I'm going to be interested in a standard Young tableau. So I have a partition lambda. I have a standard Young tableau of shape lambda. And I'm going to be interested in the composition that comes from the descent of the standard Young tableau. Okay. Okay. And there's relation between semi-standard and standard Young tableau, okay, by what we call the standardization. Okay, so when I start with a semi-standard Young tableau, I can transform it, so I can send it to a standard Young tableau by reading the entries in increasing order from left to right. Okay, so I'm going to choose the leftmost one. That's going to give me 1. Then I'm going to look at the next one and then write 2, 3. And then now I'm out of 1, so I'm going to look at the leftmost 2. Call it 4. I'm continuing in my standardization. 5, 6, 7, 8, 9, 10, 11, 12. Okay. And so this standardization works well with the descent. I can also define the notion of descent on semi-standard Young tableau. And through this standardization, if T is sent to S, then the descents of T are going to be equal to the descent of S. Okay. So this is a nice way, okay, to see why those descents are important. And then using this idea, okay, Gesell 40 years ago could define a new definition on standard of the Schur polynomial. Okay, so as we've seen before, we can write the Schur polynomial as a sum on semi-standard Young tableau of shape lambda, where we associate to each tableau an x to the t. Okay, but using this idea of standardization, now I can define my Schur polynomial index by lambda as a sum on standard Young tableau of shape lambda, but now I'm going to associate to each standard Young tableau a polynomial, not a monomial. And this polynomial is going to be indexed by the composition coming from the descent of my standard Young tableau. Okay, so now I have a more compact definition of my Schur polynomial. And here these F polynomials are quite special and very interesting. Okay, and here is an example. Okay, now if I want to write S42, I could write it as a sum on monomial on all the semi-standard Young tableau, but now I can just write the standard Young tableau, okay, and write this as a sum of F polynomials. So these F polynomials, now they're not indexed anymore by partitions, they're indexed by compositions. They are not symmetric anymore, but they're called quasi-symmetric. Okay, so this is a looser notion of symmetric. Okay, so these are polynomials whose are indexed by compositions of M, if they are homogeneous of degree M, okay, and they're quasi-symmetric. Okay, so that was my long introduction. Now let me try to explain to you how we got to that project. Okay, what would be our motivation? So our motivation is really the same things we've seen for the chromatic symmetric polynomials. We'd like to study some symmetric polynomials, okay, that have a nice expansion in the sum of the bases. Okay, so that's my thing here. Now I'm going to choose a family of symmetric polynomials that are indexed by a partition of M. They are in n variables, okay, and maybe they have some extra variables t1 up to tk, okay. And I want to look at this family of symmetric polynomials as their expansion in a sure basis, and I'd like to know, can I get some information about these coefficients, okay, that now maybe are not numbers anymore. They could be polynomials in t1 up to tk, or I don't know, rational functions or things like that, okay. And especially, I'd like to know if they are polynomials, if they have polynomials with non-negative coefficients. So that's the question, are these polynomials sure positive? Okay. And if they are, of course, as we are combinatorialists, we'd like to find a family of objects, okay, that give a combinatorial definition of these C lambda mu, okay, that are indexed by now two partitions. So in general, sometimes we can do that, sometimes we can't, and we have a whole set of techniques to prove this sure positivity. Okay, so as sure polynomials are related to the representation theory of the symmetric group, sometimes you can prove this sure positivity using representation theory. So for example, this was done for modified McDonald polynomials and LLT polynomials. But whenever you do use this technique from representation theory, you don't get a combinatorial interpretation of the coefficients. Okay, you know that they are positive or they are polynomial into positive coefficients, but you don't get the combinatorial interpretation. Okay, so you could use also things like the RSK algorithm to prove that Q-sure are sure positive. And I'm going to talk to you in a moment about crystals. Okay, so the crystal graph helps you to give some structure related to the sure polynomials. And if you can kind of build some crystal graphs from the combinatorial objects you'd like to study, you can prove sometimes sure positivity. And so this was done for a series of symmetric functions and polynomials. So for example, the Stanley symmetric functions. And then there's lots of combinatorial methods that are known, okay? And one of them is the example that I just gave you, okay, to prove that the chromatic symmetric functions for unit interval graphs are sure positive. And there was a series of overwork, so I'm not giving you all the techniques, but something that's going to be related with what I'm going to talk to you today, called the dual equivalence graph, that were built to hope to prove some kind of sure positivity, but that could only prove it into some very special cases. Okay. So I'd like to build some tools, okay, to be able to prove sure positivity, but we're going to add an extra constraint, okay? So today we want to build a combinatorial tool to prove sure positivity, but with an extra constraint, and the constraint is that I already know the expansion in the fundamental quasi-symmetric basis, okay? So I don't know the expansion in the sure basis, but I know the expansion in the quasi-symmetric basis, okay? So if I know this, okay, so here I have the compositions, I have my fundamental quasi-symmetric function, okay, and now I want to use the show expansion, okay, using the expansion from in a quasi-symmetric. Sorry. Okay. So this is not such a bad thing to do, okay, because there's examples that are very natural where the combinatorics combinatorial expansion in the fundamental is easy to write down, but we still don't understand the Schur expansion. Okay, so here I give some examples that are often coming from representation theory. So they could be the LLT polynomials, the modified McDonald polynomials, or the platism of Schur polynomials. So this is just a few examples, but there are many more. Okay. So here I give you an example. Okay, so before I told you how to write the Schur polynomials as a sum on standard Young tableau, where here we would have the fundamental quasi-symmetric function appearing. And you can easily generalize that for the LLT polynomials. So these are symmetric polynomials now not indexed by one partition, by a k-tuple of partition, lambda 1, lambda 2, up to lambda k. Okay. And now you can write them easily again in the fundamental basis. Okay, and you just kind of generalize easily what I did, what Gesell did in the 80s. Now we have not one standard Young tableau. Okay, we have now k standard Young tableau of shape lambda 1 up to lambda k, and there's a nice co-invariant statistics that you can define on pairs of standard Young tableau. Okay, and again, get the expansion in the fundamental basis. But writing the expansion in the Schur basis has been an open problem from many, many years. Okay, about 30 years, I think. And there's no big progress on that. Okay, so now it's time for me to, I guess, explain to you the subject of my talk. Okay, so this new tool that I'm going to try to present today is what we call the crystal skeletons. Okay. So it's a new tool, but it comes naturally after some recent work. Okay, so recent work on quasi-crystals. So these were ideas of Mas-Guerrier-P in her thesis, and then Montero and his collaborators that studied these quasi-crystals more from a monoid point of view. Okay, and so I'm encouraging you to read those papers. They have some pretty cool combinatorics in them. Okay, so this is not all coming from us. Really, these works on quasi-crystals were key to define what I'm going to try to explain now. Okay, so before I go to quasi-crystals and crystal skeletons, let me try to say a few things about crystals. So I'm going to set myself in a very limited case. Okay, we're just going to look at the type AN-1. Okay, but there's a whole crystal theory for many, many other things. And in particular, Kashiwara just got the Abel Prize this year about his crystal basis theory. Okay, but here we're going to be very combinatorial, so don't get scared. I'm not going to talk about quantum groups or anything. We're just going to build a graph where the vertices are semi-standard Young tableau of a given shape. Okay, so we're going to have our n, which is the number of parts of our partition. It's going to be a partition of M. The vertices of our graph are going to be semi-standard Young tableau of the shape lambda, and the entries are going to be less or equal to n. Okay, and now the edges between two tableaux are going to be labeled by Fi, which are called the raising operators. And also defining those Fi on those semi-standard Young tableaux, it's very simple and very combinatorial. So let me just explain to you how you do that. Okay, so I take my favorite semi-standard Young tableau of the day. Okay, so this is this one, where here n is equal to 4 and lambda is equal to 642. Okay. And then I'm going to ask myself, for example, could I apply the raising operator F2? Okay. So what does it mean, a raising? So it's very simple. Okay. So if I want to apply Fi, I want to replace an I by an I plus 1 in my semi-standard Young tableau. So I'm going to replace an I by an I plus 1. And sometimes I can do that. Okay. And if I can do it in a unique way. And sometimes I cannot do it. Okay, so let's see how we can do that or not. Okay, so my question here is, can I apply F2? Okay, so if you want to apply Fi to a semi-standard Young tableau, what you do is you look only at the entries equal to I and I plus 1. So I don't know if you can see them, but I highlighted all the 2s and 3s in my tableau. And now I'm going to try to pair the 2s and the 3s. Okay. So whenever I see a 3, I'm trying to pair it to a 2 that's southeast of this 3. Okay. So here I did the pairing. So this 3 can be paired with that 2. This 3 to the southeast will be paired with this one, and this 3 is going to be paired with this one. Okay. And the condition to be able to apply a raising operator is just, is at the end of this pairing, okay, a 2 that hasn't been paired. So here it's the case, and actually it's by itself, there's just 1. And so in that case, okay, then we can apply the raising operator. We take a 2 that hasn't been paired, we change it to a 3, okay, and if there are several 2s, we take the rightmost 2. Okay. So here is an example, okay, there will be in my crystal graph, okay, an arrow between this and this labeled F2, okay, and it's this 3, 2, okay, that was changed into a 3. Okay. So this is the idea on how you can build a crystal graph, okay. So you take all the semi-standard Young tableau. They are all the monomials that come in the show expansion, okay, but now you add on top of it this graph structure. Okay. So here is an example. If lambda is equal to 2, 1, and n is equal to 3, okay, so you can list the semi-standard Young tableau of shape 2, 1 with entries 1, 2, and 3. Okay, you can see that there's 8 of them. Each of them gives you a monomial, but now you can build this crystal graph. Okay, so you don't only get your 8 tableau, but you get a structure, an algebraic structure on it. Okay. So that's my crystal. Okay, so we have a partition, and we have an n that tells me the entries, and I have my crystal graph. Okay. So now what's a quasi-crystal? Okay, so now the quasi-crystal comes from the notion of standardization that I defined you. Okay, now I'm going to take, for each of my semi-standard Young tableau, I'm going to associate to it, I'm going to standardize it, I'm going to associate to it a standard Young tableau. Okay, and I'm going to group together all the semi-standard Young tableau that give the same standard Young tableau. Okay, so I claim, so if I standardize these 4 tableaux, okay, they all standardize to this standard Young tableau, and I take the subgraph induced by this set of tableaux. Okay, so as you can see on this example, this graph is connected, and it's always going to be the case. Okay, so here if I take the other standard Young tableau of shape 2, 1, I get another quasi-crystal. Okay, and it's a theorem of Mas-Guerrier-P that each quasi-crystal is also isomorphic to a crystal graph of a smaller shape. Okay. And also, if I sum, just using Gesell's theorem, on all the tableaux coming from a quasi-crystal, okay, I get back my fundamental quasi-symmetric polynomial. Okay. So now we know what a crystal is. We know what a quasi-crystal is. Okay. So I can define now what's a crystal skeleton. Okay. So it's going to be a contraction of the crystal graph where each quasi-crystal now is just smoothed to just one vertex. Okay. So I take all the tableau, the semi-standard Young tableau that's standardized to the same tableau, and I just make one vertex, okay? And I take all the tableau that's standardized to the other semi-standard Young tableau. I get another vertex, and then my crystal skeleton graph is a graph where the vertices are going to be standard Young tableau, and then I'm going to put an edge between two vertices here. Is whenever I contract here, I have an edge between the vertices, okay? So I just do a contraction of a graph, and that's what we call a crystal skeleton, okay? So, yes, it took me 35 minutes to define my title, so bear with me, okay? So, okay, so as you can see, this kind of really contracts the information, okay? Because here I gave an example of the crystal graph for the shape 3-1, okay? So you can see that the crystal graph is already quite big, okay? Crystal graph can make really big, but here, when I take the standardization, okay, so all those tableaux are going to standardize to this tableau, all those to that one, and all those to that one. Okay, and finally, my crystal skeleton is just going to be a graph on 3 vertices, which are exactly the standard Young tableau of shape 3-1. Okay, and then now if I want to have the show expansion, okay, I'm hoping to use this crystal skeleton. Okay, so now let me just recap what we want to try. Okay, so we fix a partition lambda of M, okay, and we build a graph where the vertices are standard Young tableau of shape lambda. And to understand the graph, we need to label the edges by intervals, okay, of integers, and these intervals have an odd size, okay. So they're just going to be indexed from I plus 2k. Okay, so they can also be indexed by cycles, but I don't think I'll have time to explain that today. Okay, so here is an example of if lambda is 3, 3. So you all know that the standard Young tableau of shape NN is counted by the nth Catalan number. So we have 5 standard Young tableau of shape 3, 3. Okay, and if we do exactly the procedures I give you, okay, where I contract my crystal graph, I'm going to have this thing that looks very different from a crystal, because now, for example, I can have cycles in my crystal skeleton. Okay. And so the goal of our paper, okay, I'm going to give you a few hints about the properties of this graph, is to understand what those graphs are and how can we characterize, how can we see that a graph, okay, is indeed a crystal skeleton. And if we can understand that, okay, we hope to use that to prove show positivity of certain polynomials. Okay. So there's many nice things about this graph. So I hope I can convince you of a few today. Otherwise, I encourage you to look at the paper that's on the archive. So first of all, inside our crystal skeleton, okay, the same way that quasi-crystals are isomorphic to certain crystal graphs, we have also crystals as subgraphs of our crystal skeleton. Okay. So for example, a crystal skeleton of shape lambda, it contains B lambda, so the crystal index by lambda, and here where the index is the number of parts of the partition. Okay. So before I showed you the crystal of shape 2,1, and you can see that here we find a graph that's isomorphic to the crystal of shape 2,1. Okay. So even though we contract from the crystal to the crystal skeleton, okay, inside the skeleton, we still find some of the crystal graphs. So the structure is still quite difficult, okay? And then I told you about the dual equivalence graph before, okay? And we can prove that the dual equivalence graphs are actually a subgraph of the crystal skeleton. Okay, so these were defined by Heyman and studied by Asaf, and Roberts could make the work of Asaf complete, okay, and show some axioms about this dual equivalence graph. And they were used to prove that certain LLT polynomials were show positive, but they were only for very special cases where, like, there's a statistic on the tuple of partitions called a diameter, and the diameter must be less or equal to 3. Okay. And actually, let me just tell you how you can find the dual equivalence graph inside the crystal graph. Okay. So I told you that the edges of the crystal skeleton are indexed by interval of odd length, okay, of size 2m plus 1. And the dual equivalence graph is just a graph where we only keep the edges where the intervals have size 3. Okay, so if I delete all my longer edges in my crystal skeleton, I get back to the dual equivalence graph. Okay, so that's what's told us that maybe this is a good tool, okay, because it's a graph that gives you more information than the dual equivalence graph. And we are hoping to use that to be able to say things about LLT polynomials. Okay, so again, we can really understand what's going on in that crystal graph. So for example, so I said the vertices are indexed by a standard Young tableau. And from a standard Young tableau, we can get a descent composition, okay? And we can write down some necessary and sufficient conditions so that we have an edge between two tableaux. Okay, so for example, there could be an edge between a tableau T and a tableau T prime indexed by I, okay? Only if I, okay, is, so let me try to say that in a simple way. Okay, so if I look at the descent composition alpha, okay, and I put I on the descent composition, okay, it only is on two parts of the descent composition. Okay, so for example, here I have the descent composition 3, 3, okay, and I can see that I can go out with 1, 5, okay, which is just on two parts of my composition, or on 2, 4, which is also on two parts, okay, where here the middle of my interval is on the first part of the composition. Okay.
Here alpha and t are related or not at all? I mean, it's for all t and all alphas.
No, alpha is given by t. It's a composition that you can read on the tableau. Alpha is the
composition of t.
Yeah, yeah.
Okay.
Yeah, yeah. So alpha, yes, just depends on t. And also, okay, when we have an edge between two tableaux, so again, alpha and beta are just information coming from the tableau, okay, we can say that whenever the I, okay, is on the two parts here and just on the two parts, then we'll always have an edge unless before, okay, incoming from alpha, then there's an edge indexed by j, where j is a subset of I, and then we have some kind of order between the two compositions, gamma and alpha, which is a classical order on composition called the domination order. Okay. So we know when an edge can appear, and we know also when an edge is forced to appear. Okay. And then there's many things we can say. So I'm going to try to say a few things. Okay. So if the composition coming from T is of length L, so it has L parts. Okay. Then the length of the composition of the tableau T prime will have exactly the same number of parts, one less or one more. So here I just wrote the descent composition. I didn't write the tableau, but you can see that here I can go from 3, 3 to 2, 3, 1. So I can gain one part, okay, basically, or here I can go from 1, 2, 1 to 1, 3, 2. So I can lose one part, or I can go from 2, 2, 2 to 1, 3, 2. And so I can keep the same number of parts, okay? And when the number of parts is conserved, what I have is kind of so one part is just giving one to a part to its right. Okay. So here 2, 2 becomes 1, 3. So the graph has some very, very nice structures. Okay. And also the same thing that's known for crystal graph. There's an involution on the vertices of the graph that actually reverse the descent compositions. Okay, so whenever we have now I call my tableau V and W, but whenever we have an edge from two tableaux, okay, we can see that there will be an edge when we reverse everything. Okay, so we can apply the Lustig involution on the tableau. We are going to get a reverse of the descent composition, and we can reverse the interval, and we find that edge. So for example, here I have an edge from 2, 3, 1 to 2, 2, 2, indexed by 4, 6. And that means that somewhere in my graph, I'll have an edge from 2, 2, 2 to 1, 3, 2, where I reverse the interval and I get 1, 3. Okay. And this is true all over my graph. We have this involution that reverses the descent composition. Okay. And then something that's pretty nice also is we have that notion of fans. So whenever we have a long interval, so here, for example, 1, 5, okay, of shape of size 2m plus 1, then we'll have also a shorter edge living like that of size 2m minus 1, where the intervals are nested, okay. So these will give me a sequence of edges like that ends with a cycle here. And then these vertices would also be joined by certain edges of size 3. Okay. So this is also some very nice combinatorial setting coming from those graphs. Okay. And so we define like that some axioms that define exactly our graph. Okay. And we have 3 types of axioms that I'm not going to explain in detail, just give you a couple of insights. Okay. And so these are related to the theory of the symmetric group. So the first type of axiom is the GLN branching. The second is the SN branching. And the third is local axioms that were also defined in the terms of crystal graph by Stembridge for certain crystal graphs. Okay, so let me just give you, in a couple of minutes, I still have some insights about these two, just some ideas. Okay, so first, the SN branching. It's a very, very nice property of the crystal graph. Okay. So, for example, now if I look at my crystal graph and I delete all the edges that contains m in the interval. So here it's the case m equals 6, because we have a partition of 6, 3 to 1. Okay, so if I delete all the edges that contain 6 in the interval, okay, let me try again. So I'm going to delete this one, this one, this one, this one, this one, and this one. Okay, so I'm going to disconnect my graph. Okay, and this graph now is going to be a union of smaller crystal skeleton graphs. Okay, namely, if my shape is 3 to 1, like in my example here, okay, I'm going to find all this crystal graph where I can take off one box of my partition. Okay, so I could take off this box and get this 2, 2, 1, okay, or this one get 3, 1, 1, or this one get 3, 2, okay, and I find the union of my smaller crystal graph. Okay. And the local axioms, so as I just said before, okay, local axioms were defined by Stembridge for the simple lace case. So Stembridge could show that whenever you have a tableau with two exiting arrows labeled Fi and Fj, okay, only very few things can happen. If I and j here are different, so actually they have to be different, then the only thing you can see in the graph is a square or an octagon. So we've seen the octagon in the case of shape 2, 1, okay? And if you see an octagon, then j has to be equal to I plus 1. Okay, and we have a similar things coming up in the case of the crystal skeleton, except now things are a bit more complex. Okay, we don't only have a square and an octagon, so we still have the square and the octagon actually coming from crystals, but we can find also some triangles and some pentagons, okay? Not hexagons or anything, okay? And we have also that notion of fans that we defined before, okay? And so actually we can put together, okay, all these combinatorial things coming from crystal skeleton and prove that actually if we find a graph with a certain list of axioms, okay, that can come from GLN, from SN, or from our local axioms, when we can uniquely characterize whether a graph is a crystal skeleton or not. Okay. So now what we are doing, okay, now that we build, okay, this nice new tool, okay, this nice new tool from crystal skeleton, is we're going to try to use that to find some applications. Okay, so we started working on that this summer. And I hope that soon I can tell you that crystal skeletons are very cool and can be used to prove some show positivity that we didn't know before. So thank you for your attention and thank you for listening.